Thank you for the introduction. I'm Grigor. I'm currently working at ModelFront, but today I will talk about my research, like part of this from my research during my PhD thesis at Aix-Marseille University, and it's about uncertainty quantification, or when AI models learn to say, I don't know. So I will start the presentation with the general context and motivation. What is uncertainty, why it's important, why we need to learn it at all. Then I will present you basics of one of the approaches for uncertainty quantification, and in general, in the multimodal scenario, how do we quantify, what challenges we have, what problems we may have. At the end, I will conclude and give some remarks about the future of this field. So the idea of not knowing something, of identifying that we don't know anything, is not new at all. Even from ancient times, from Socrates, we know that he said, I know that I don't know anything, but others, like his competitors, didn't know even that. They claimed that they know, but they didn't know anything. And that's actually a very big issue for us, for humans, in this era, but it's even worse when we come to AI systems, to AI decision-making agents. And that's bad because in today's world, most of our decisions are somehow influenced by AI systems. We already use autonomous cars. Okay, we don't do it here yet, but maybe soon. But in the US, they already do. So the car decides where to go, where to turn, where to speed up, where to slow down. We shall not, but we often ask advice to AI agents for medical stuff, or allow it like full autonomy for our code bases to run commands, to delete databases, I don't know, to execute lots of things. Or we translate stuff and then we send the translations without verifying, without checking. And we all understand how this can be problematic, right? We have all seen this, sorry, I was mistaken, yes, you were right. And sometimes it's harmless, sometimes it can be really harmful. For example, if it's just a smaller device, it can be harmless, but if it's a medical device or if it's a car that speeds up instead of slowing down, it can be really problematic. That can also be problematic for translation if you are like in medical field or in high-stakes decision-making, where small mistranslation can often lead to catastrophic results. And these are not just hypothetical situations. There were cases, for example, for Tesla, where its decision-making led to fatal accidents. And so leaving all of the decision to current AI systems can be quite dangerous and quite problematic. So what would be ideal is if our AI systems could understand when they're uncertain, could know when they don't know the answer, and could leverage the decision-making to us, humans, or ask for additional information, and then make a decision based on this additional context, or leave the decision to us entirely. The things get even worse at multimodal situations. So let's say we have an autonomous car and it has sensors like lidar sensors and the camera for decision making, and it sees like a wall painted as a road, right? And the camera says, okay, it's fine, you can go forward, but the lidar sensor says, no, it's a wall. And the AI systems now come to a decision point where it doesn't know what to do, because it has two modalities, both are quite sure what the decision shall be, but the joint combined decision is really hard to make because of the conflict. So what we would like actually to have is to be able to, for unimodal cases, to quantify the uncertainties in AI decisions, to give the options to AI agents to say, I don't know, please make a decision instead of me or give me more information. And for multimodal cases, to understand the confidence of each modality, the amount of conflict between the modalities, and be able to either resolve this conflict or return a high uncertainty so that human can do something about it. So how do we do that? How do we quantify the uncertainties, or what do we mean by the uncertainty? Let's talk about it a bit. So here we have the standard AI, like deep learning decision-making system. So here we have just an image that passes through our neural network. We pass it through a softmax activation layer and get the probabilities. We all know this, it's like quite simple. But one thing that we don't often know is that it's shown that these systems, these softmax-based deep learning models, can be very overconfident, which means that they can make incorrect predictions with very high probability. And this can be quite problematic. We need to understand when the model is incorrect, it shall be quite uncertain about its prediction. And that's actually what uncertainty quantification is all about. It allows us to introduce a level of uncertainty. So if a model sees something that it's not quite sure about and can be mistaken about, it says, okay, I think it's a road, but I'm more uncertain about it. So you better give me additional context, or you make decision for instead of me, right? But where do these uncertainties come from? In general, there are two types of uncertainties that are distinguished. The first type is called aleatoric uncertainty, or data uncertainty. And this comes through the inherent randomness or noise in the data. So here you can see that the data is mixed here. So we cannot, with any kind of model, make an accurate prediction for this point right here, because it is quite uncertain. We don't have enough, we have mixed data, so we cannot make a perfect prediction here, right? And this is also called irreducible uncertainty, because even if we collect more and more data, we cannot reduce the uncertainty here. The second type of uncertainty is called epistemic or model uncertainty. And that's the uncertainty due to lack of knowledge. For example, here you can see that we don't have any data points here or around in the points. So if we have to fit a model, we don't know which model is the correct one. So if we have a point right here, we don't know what the label shall be because we don't have enough information. And this is in fact reducible uncertainty, because if we collect more and more data points, it will reduce to essentially zero. If the data number goes to infinity, like the number of samples goes to infinity, this uncertainty goes to zero, or ideally it should. And there are actually different approaches and lots of different ways to quantify these specific types of uncertainties, because it's quite helpful to understand if the uncertainty comes from data or comes from model. Unfortunately, it was recently shown that the current approaches that are trying to quantify or disentangle these epistemic and aleatoric uncertainties, they don't really do it well enough, because we have almost one correlation between these two uncertainties, as you can see here. And that's a problem, because it essentially means that these both uncertainties are kind of showing the same thing, while they shall show something different, right? And for that reason, we today are not going to concentrate on disentangling these uncertainties. We are going to concentrate on just one uncertainty measure. But hopefully in the near future, because this is a very active area of research, in the near future there will be more research done and more better approaches to quantify these uncertainties. And in general, for uncertainty quantifications, there are also different types of approaches which can be separated into 4 categories, non-exclusive categories. There are Bayesian approaches, deterministic approaches, ensemble-based approaches, and augmentation-based approaches. Bayesian-based approaches are very beautiful to formulate. They are very interesting and very, mathematically and very in a beautiful way, represent both types of uncertainties. But as we know, doing Bayesian inference in practice is not really tractable, and the approximations are quite hard to compute and don't give enough estimates. So I'm sorry for all Bayesian people here. We are not really going to concentrate on Bayesian inference today. But we know that for Bayesian, we need to do multiple passes for inference, right? In deterministic approaches, that's the inverse. We want to do only one pass through the network. We want to do a deterministic pass through the network and get our uncertainty estimates. For ensemble-based approaches, they are actually quite simple to understand and to implement. We developed an ensemble of networks, and we get different predictions from each network, and the variability between the decisions gives us a notion about the uncertainty. But the issue is that, again, we have to train multiple networks, we have to maintain multiple networks, and that can be quite expensive. The augmentation-based approaches are trying to modify the inference data a bit to understand how the probabilities change. But that's also quite expensive in inference time, and also it depends highly on our augmentations. So today we are going to concentrate on deterministic approaches, or more specifically on subjective logic-based evidential deep learning, because it's computationally very efficient. It requires very minimal changes to our existing architectures, and also it provides explicit and interpretable measures of uncertainty and beliefs for each class. We'll go more into this now, so you see how it works. So again, if you go to our standard classification, right, we have the input, we pass it through a neural network, then through a softmax function, and get our probability estimates. If you put it on a probabilistic simplex here, we are going to get just one point, right, towards the road because it's the highest possible class. The point is right here. However, if we train this network from the scratch again and make this prediction again, the probabilities are not going to be exactly the same, right? They are going to be a bit different. And if we do it multiple times, we are going to get deep ensembles, which we talked about briefly. And it's going to give us a small distribution right here. So if this distribution is like concentrated like this near a point, it means that the model is confident. If it's spread around, it means that it's more uncertain. But as we talked, these deep ensembles are quite complex because we need to train and maintain multiple networks. So researchers thought, and in this case, Sensoi thought, okay, why don't we just try to model the distribution from the get-go and predict the parameters of some distribution? And for distribution, they decided to choose Dirichlet distribution, which is a distribution over this probabilistic simplex. And each sample from this distribution gives us one categorical standard, like a probability distribution. I will not go into too much details about Dirichlet distribution, but it's basically parameterized by k parameters. And in this case, if you have k classes, let's say 4 classes or 3 classes, we'll have 3 parameters. And each parameter kind of will represent the amount of evidence, the amount of information we have for the specific class. If we have a Dirichlet 1, 1, 1, so we have one belief for each class, it's going to be total uncertainty, or the uniform prior. And as the belief towards like evidence in one class increases, as you can see here, the model gets more and more confident towards a specific class. And with this Dirichlet distribution, with this modeling, we can model the both types of uncertainties. We can have confident prediction. We can have aleatoric uncertainty. You can see the model is very confident here, but it doesn't know which class it is. So it knows that it doesn't know something. Like it knows that it knows, but it knows that it doesn't know. It's kind of a bit paradox, but it's what aleatoric uncertainty is all about. We know the model has seen the data, but it cannot make a decision because all classes are equally probable. And the third case is the epistemic uncertainty, where the model just doesn't know anything. It's just total uncertainty, right? It hasn't seen enough data. But how can we represent this uncertainty in an interpretable and understandable way? For that, we are going to do a quick small detour to subjective logic, which is a small extension, not small, but an extension of probability theory. As we know, in probability theory, the probabilities sum up to 1, right? But in subjective logic, they do not sum up to 1. They sum up to a value between, at first we don't have probabilities, we have belief masses, which sum up to a value between 0 and 1, and the rest is the uncertainty. So as you can see in subjective logic, unlike in probability theory, we have uncertainty included in the decision framework from the get-go. So if we model our neural networks through subjective logic, we are going to have uncertainty in the decision from the beginning. So how can we connect these two together? How can we connect the Dirichlet distribution with the subjective logic? Turns out that there is a nice mapping, bijective mapping between these two notions. We have the parameters of Dirichlet distribution, and if we remove one from them, we will get a thing called evidence, which kind of shows how much evidence we have for each class. If this evidence value is high, the model is more confident towards that class, and if it's low, it's less confident. From it, we can just normalize these evidences and get the belief masses for each class, and the rest will be the uncertainty. As you can see here, the S here is the normalization factor, or Dirichlet strength. It's called Dirichlet strength because it shows the amount of evidence, total evidence we have. So if it's higher, because it's in the denominator, if it's high, we have more confidence, so less uncertainty. If it's low, we have less confidence, so more uncertainty. So just putting all of them together like a Lego pieces here, we have the neural network. It's predicting, instead of probability estimates, it's predicting the parameters of the Euclid distribution. So we just switch from logits to parameters of the Euclid distribution here. And from it, we can get this distribution. And through bijective mapping, we can get to subjective logic-based belief masses and the uncertainty, right? So in this case, if one class has very high belief mass, we are just going to choose that class as the prediction. Conversely, if they all have low uncertainty, low belief masses, and the uncertainty is quite high, we are going to say, okay, I don't know the answer. I'm elevating this to a human, or I'm trying to gather more evidence. And that's something called classification with reject option. So essentially, we provide the AI with ability to say, I don't know, which standard deep learning models do not have. In multimodal scenario, things get a bit more complicated because now we have several modalities and we get representations from different modalities. We need to combine, to fuse these representations together and get through to a final classification, right? And there are different ways that we can handle this. There are approaches where we can combine these modalities at the very early stage as raw modalities and do standard classification. We can combine their deep features. So it's after the feature extraction phase, we can fuse them together. It's called intermediate fusion. And what we are going to talk today about is called late fusion, where we make the predictions from each modality and then fuse the predictions of different networks. Yeah, like this. But here we have the problem, right? Each modality can have different amount of information. So one modality can be more confident, can be more informed, and the other can be less informed and more uncertain. And also they can often have conflicts, as we discussed before. Sorry. As we discussed before, they can be in conflict, and that can cause problems in decision-making process. So our final uncertainties need to reflect the fact that the modalities could be uncertain, or there could be some issues, some conflicts in decision-making process. Before going too much forward, let's understand what we mean by saying conflict, because we understand it at the language level, but we don't know how we define it in mathematical level, right? So there is this notion of degree of conflict in subjective logic, where we define the conflicts, the situations where we have low uncertainty and different predictions. So the modalities are confidently disagreeing, right? As you can see here, in both cases, both modalities have very low uncertainty, so they are very confident, but they predict different classes. And this part is very important because if either of the classes, if either of the modalities is uncertain, then we do not have conflict. We do not have conflicting situation. And that's logical because let's say if we are arguing together and you are very confident in your discussion, in your ideas, and I know that I'm uncertain, then we are not really arguing. I will say, okay, you know better, you are correct, so there is no conflict here. But if we are both disagreeing, if we are both really sure about our ideas, then we are going to have high conflicting situations. So what we want to have in our multimodal decision systems is to be able to quantify the uncertainties in each modality and increase the uncertainties when we have high conflicting situation, and have still very good performing models and improve source reliability detection. What this last point means is when we have conflictive situations, when we have problems in decision-making process, our uncertainties shall reflect that. So in final decision point, humans shall know, okay, there was some issue here. I shall be more careful when making decisions in this case. To do that, we can use a notion we suggested called discounted belief fusion, where we have different modalities, and the modalities can disagree. They can be in conflict, as you can see here. So both of these modalities agree, while the second modality disagrees with them. And then we try to model it in a similar way. We try to say, if one of the modalities disagrees with different other modalities, then probably that modality is the incorrect one, right? If all of you here are agreeing about some topic, and I'm the only one that disagrees with you, then I'm thinking, okay, maybe I am the wrong one, maybe you are the correct one, so I'm increasing my level of uncertainty. And as you can see in the final prediction here, the second modality has more uncertainty. It's increased its uncertainty because it's disagreeing with the other modalities. And the way we are doing that is first we compute an agreement matrix between the modalities, which is basically first we discuss, compute the pairwise disagreement, pairwise conflict. And just 1 minus this conflict, we get the agreement matrix. So in the agreement matrix, if there is a modality that disagrees with different other modalities, with more other modalities, its scores are going to be lower, right? Or here. And if you get the product over the rows or the columns of this matrix, the modality that is disagreeing with many more other modalities is going to get lower score here. We call these scores discount factors. And then we take our initial beliefs and the uncertainties, and we readjust them so that the modality that has lower scores, lower discounting factors, is going to readjust its belief mass so that its uncertainty is higher at the end. Yeah, right here. So you see the discounting factor is low here, as 0.18, which means we are going to move 82% of the belief mass from here to the uncertainty. And then when we fuse these modalities together, these beliefs together, we are going to have less impact from the third modality on the final prediction because it's more uncertain. And we are going to have higher total uncertainty at the end. Sorry. If you want to put it to a code, it's actually quite small. We just compute the pairwise conflict, the agreement matrix, the discounting factors, and then we just readjust the belief masses and the uncertainty and compute the final alpha parameters for the Dirichlet distribution. Let's go over a toy example to understand what's going on, right? So this is actually a very famous example of high conflict situation from 1979 by Zadeh. And he said, okay, let's assume we have two modalities or two opinions and three possible classes. The first modality, or the first doctor, say, thinks that the first class is very probable with 99% belief mass, and thinks that there is a very slight, very small chance that the third modality is actually correct. The second modality, or the second doctor, thinks that the second class is more probable, is very probable to be true, while he also thinks that the third modality, third class can be with very slight chance can be true, right? And they both have zero uncertainty, so they are both very confident in their predictions. Old or other fusion algorithms are not handling well these kind of situations. So we can see there is an algorithm called belief constraint fusion, where it takes all of the belief mass and puts on the third class. Why? Because it says, okay, I know they are disagreeing, but they are agreeing on the third class, so it means that the third class is the correct one. Although they both think that the third class is not very probable, but that's the only thing they agree upon, right? This can work in some situations, but let's say you are going to doctors and both doctors think that you are really unlikely to have this kind of disease. But because they think, okay, there's a slight chance, you are saying, okay, 100% I have this disease. That's not really how it works, right? There are other fusion algorithms are actually dividing or spreading the belief mass between these two classes, which is more logical, but still doesn't give us a good decision system because we still have zero uncertainty. And as we can see with the just discussed discounted belief fusion, most of the belief mass goes to the uncertainty, so we know that there was some problem, there was some issue, and our prediction is more uncertain, so we can gather more information or leverage it to human. Going to a more real-world data sets, we have the Luma dataset here, where we have two modalities, and both modalities are very confident. You can see that they have very low uncertainty. And we introduce some artificial conflict in these modalities, in these classes. We can see that the other belief fusion algorithms, they do not really well separate between the conflictive mass in the yellow, in orange, and non-conflictive mass in blue. Yeah. But the discounted belief fusion puts a very good separation between samples that do not have any conflict and samples that have high conflictive situations. This is an example of another data set where we have very high uncertainties in modalities. And as we discussed, when we have high uncertainties from the get-go, we do not have conflictive situation anymore, right? So in this case, the modality already have high uncertainty, so there is no any reason to, we cannot increase them any further. So that's why we do not have any separation between the conflictive and not conflictive masses anymore. They're all just uncertain. Okay, so we talked about uncertainty quantification in unimodal and multimodal scenarios. We talked that the uncertainties are quite important in especially safety critical areas like autonomous driving, finances, healthcare, other areas, and that we need to be able to confidently make predictions or reject these predictions and elevate it to human decision making. We also discussed multimodal cases where you can have conflicts between modalities. And we discussed how we can resolve these conflicts or increase the uncertainties when we cannot resolve the conflicts anymore. So what's next, right? We discussed only classification situations, but now the trendy part, the part where more ML people are going is large language models and autonomous agents. And these are also quite problematic because they are making lots of decisions, lots of suggestions to us. And they also need to be able to quantify their uncertainties. So what actually I think shall be the future focus of uncertainty quantification in LLM-based systems is to discuss how we can combine LLM-based decisions in multimodal agents for final decision making. So if you have different agents that they are taking information from different sources, often incorrect sources, often uncertain sources, this modality-based agent shall be able to understand, to quantify where they don't know anything, and either get more information from different sources, or say, okay, I don't know, so I'm not going to delete this database, I'm not going to make this right turn here, and I'm going to give human the option to do this. Yeah, I want to acknowledge my collaborators on this project, Sana Salami, Lau Berti-Quil, and Sebastian Fournier. And I will be happy to answer your questions if there are any. Thank you.
My question is, isn't it easier and more reliable to train model? For example, you mentioned models like projects like autonomous autos or some, for example, LLMs. Isn't it just easier to train a model to understand what is uncertain during the training process without static math? And like in, for example, with reinforcement learning, we can penalize him or reward if he understands if something is uncertain.
Thank you, and that's actually a very good question. So one thing about uncertainty quantification is that it's unsupervised, right? we do not have labeled database to know, okay, this case is that model shall be uncertain, and this case is where model shall be correct. What we know is that when model is making incorrect decision, they shall be uncertain, and vice versa. And also for reinforcement learning, we can cover some situations, but that's only like some limited amount of situations we can cover. There are lots of different situations when the model can encounter, and especially with out-of-distribution data, with in situations where it never been before, that the model can be uncertain, doesn't know about it, right? It's really hard for standard supervised learning. We need to have a labeled data set. We don't have that. So what we try to do is we try to estimate the uncertainties or train the models in a specific way where they understand when they are uncertain at the inference time without any labeled data set. Thank you.
When you are working with multimodal systems, are there any way to estimate how those uncertainties are reasonable? What I mean by this, can it give you some source of signals to eliminate one modality? Maybe it introduces some uncertainty which you don't need a model to be less confident.
Thank you. And yeah, that's a very good question too, because let's go back. Yeah, so that's essentially the goal for our fusion algorithm here. So if the model has very high uncertainty, we don't want it to anyhow affect our decision making, right? So that's why here we increase the uncertainty of that modality. And in fact, the final fusion function is weighted by the uncertainties of the modalities. So if one modality has high uncertainty, it's not going to have much influence on the final decision system. And if it's very confident, it's going to have more say in the modalities. But of course, that's a very good signal. So if we have often modalities where we have high uncertainty, we may say there may be something wrong with this modality. So we may decide to remove it from the decision process at all, or we try to reannotate the data. We try to, in fact, like there is a field called active learning where people try to have, when they have limited resources for labeling, they try to understand on which samples they have more uncertainty and take these samples and relabel them, and in that way retrain the model to have more confidence in these scenarios, in these situations. Yeah.
Thank you for the talk. I have a question which might be super simple, but I was thinking about those scenarios where we have multiple modalities and some of them are more important just from the get-go than some others. And when we just come to the predictions at the end, it's more or less easy to like reweight them because of their importance. And I was thinking how easy, is it that easy to also kind of reweight the uncertainties of those modalities?
Thank you for the question. It is easy to reweight the uncertainties here, but we need to do it carefully. Like we can weight the decisions based on our notions of importance, right? But for uncertainties, the uncertainties need to still mean something when we reweight them, right? So if you artificially change the uncertainties, they may not reflect the actual confidence of the model anymore, and that could be problematic. So we can, my answer would be we can reweight them as far as they kind of fit in our definition of uncertainty, because there can be different definitions. And also we can still just reweight the predictions and not touch the uncertainties due to our prior beliefs and information. And in fact, the fusion functions give us like that. I'll try to find it. Okay, I don't have the slides here, but there are like fusion functions that have these weights where we can just integrate the weights into the fusion function based on our beliefs and kind of readjust the final predictions.
I was curious to know, is this approach scalable? Let's say we have more than 3 like types of classifiers, and we have like, let's call them experts, more than like 2 or 3. Do we approach it the same way with the small scale version?
Thank you, and that's also a very good question, because there is one issue with this approach that you proposed. Like, there was one issue. Let me get back. Here, when we get the product of these conflict masses, right? If we have too many modalities, and all of our disagreement scores are between 0 and 1, this final product is going to go to 0. So essentially, we are not going to get any, we are going to get very high uncertainty for all of the probabilities. So that's why here, when we compute the agreement matrix, we integrated a strength of discounting factor, which basically says how much conflict shall, how much the beliefs shall readjust based on the amount of conflict. So if you have too many modalities, this is a hyperparameter which we can tune to still reflect the same amount of readjustment, but without taking the uncertainties to 0. Another issue was that this part, this pairwise degree of conflict computation, has quadratic cost, right? And if you have like 1,000 modalities, it could be a problem. But in practice, we very rarely have, like, we have 4, 5, 10, okay, but not more amount of decision makers. So in practice, this is not a real issue. Thank you.
Thank you very much for the interesting talk. Could you please explain again, when we train a usual neural network, we get this log probabilities for softmax, and essentially it's already show confidence of the model. So if you have one high class, it means model is certain in this prediction. If we have, for example, 2 classes which have good probabilities, it means model is uncertain. So what's the advantage of moving from these log probabilities to Dirichlet distribution?
Thank you. So you are right that the softmax probabilities are meant to present the confidence, but that's is shown first with this paper that it's not really the case in practice. So essentially, when the deep neural networks were presented at the beginning, they were more or less calibrated. So their amount of probabilities were actually more or less reflecting the amount of confidence they had. But nowadays, with deep neural networks, that's not the case anymore. They are trying to, we give them the task, and they are trying to overfit the task in a way. And for very slight changes, they can scale the probabilities like very drastically. And they can have very high probability for incorrect class, which can be an issue. So the idea of uncertainty quantification is, in fact, to change that, to have an uncertainty score that actually reflects the amount of uncertainty they have. And even in their experiment, you can do like several passes in the neural network, right? Yeah, and get different scores. And that already means that your one experiment, your one training sample was not really reliable. Your one softmax scores from one model was not reliable anymore. Because if you change just the training process, just retrain again, it's going to give you different probabilities, right? Thank you. Thank you.